U mean, and then we create that we can like rearrange like this. Then P del X Q bar plus the del del X tau X this one minus rho U dash square plus del del Y tau Yx bar minus rho U dash V dash plus del del Z tau Zx minus rho U dash W dash mu. And then we said that this the tau capital Xx involves the velocity gradients or the mean velocity gradients rather, and these are the terms which are arising because of the momentum flux due to the fluctuating components. These are actually not stresses. However, when Reynolds did the decomposition and like rearrange this, just to honor his name, these components are the Reynolds stress, and we also yesterday wrote the matrix form. So minus rho ui qz dash, and we wrote down the total matrix minus rho u square u dash v dash u dash w dash. Similarly, this one, the diagonal components v dash square and w dash square is right like this. Then v dash w dash here and v dash u dash here. Then w dash u dash and w dash v dash here. So these are the components of the Reynolds stress. And then we said that like these components are equal to each other. So W dash V dash these are. So there are 6 unique components, and we said that like due to the evaluation procedure, there are these 6 new components. We have no way to know their like quantities, how to estimate them. And we said that if you want to get another governing equation regarding these quantities, you will generate some quantities involving again like this rho ui ug uk. So you can see the problem is never solved, and like the number of governing equations are always less than the number of unknowns. So then we said that it is a turbulence closure problem. So after that, like that was the last yesterday's discussion, and then like today we will like show here these quantities are anyway we know that u dash square, v dash square, w dash square, those will be the negative terms. But in general, what about minus rho u dash v dash? So a very simplistic model of let's say a flow over a wall where the u direction velocity is like a function of y. So let's say at a given height y1, this is uy1, a little higher height uy1 plus l, and a little lower height uy1 minus a. So now let's imagine there's a fluid element here in the intermediate flow, and the fluid element, what if like there is a positive fluctuation of the velocity, which so here the fluid element, let's say there is a positive velocity fluctuation, which implies that the fluid element will basically go to the upper portion. So when this fluid element goes in the upper portion, essentially this fluid element with its lower u velocity mixes here, right? And then since this is lower velocity, the overall velocity, like the u component, that will decrease due to the mixing of this region. So here u will decrease because this component have a lower u velocity. So then, like you can say, u dash is negative and this one is positive. So u dash v dash is here. The product is negative, right? Now, on the same logic, let's say by a negative velocity or a negative velocity fluctuation, it goes down. So when v dash is negative, let's say the fluid element goes down here. Now, in this case, this has higher u velocity. On mixing, the overall u will increase now. So then, since u will increase here, this u dash fluctuation will be positive. So overall, again, v dash u dash is negative. So in general, u dash v dash is negative, and then minus rho u dash v dash when you do the averaging procedure turns out to be positive due to the negative sign here. So this is a very simplistic picture of showing. Obviously, it's not that rigorous. You can always argue that only it is like in the without any wall how you prove, but this is just a simplistic picture to show that in general the u dash v dash will be product will be always negative. Okay. So then now earlier, like if you remember, we said that like the del x tau xx plus del y tau yx plus del z tau zx. If we individually write, we can, let's say we take the t component here plus this will be 2 mu del u del x plus del y mu into del u del y plus del v del x. Similarly, this one del z will be del u del z plus del w del x. So the pressure component is as it is minus del p del x plus we can rearrange one, like we take the mu outside assuming that it is constant throughout the fluid. So del u del x, we just write down 2 del u del here. We write like this. One is del 2 u del x square, and one we are writing like this mu del x del u del x. Okay. Then this one mu del 2 u del y square. This one we are interchanging each other and we are writing the del x outside. We are writing like this del v del y. Following that, here there is mu term here anyway, and mu term here also. So mu del 2u del z square plus mu, again we do the interchange here del x del w del z. Now if you look these components in an incompressible flow, we take the del x, we can write del 2u del x, del u del x plus del v del y plus del w del z. This term is nothing but the divergence of velocity field, which is equal to 0 for the incompressible condition. So thereby we are finally left with these terms minus del p del x plus all the second order derivatives of the u component. So this we can write mu Laplacian of the u component. Similarly for the y1, this is for the general one. I am not going into the averaging procedure still now. this will be V, and the next one will be minus del Z plus mu Laplace in the W. So these are the general components. So this part is clear that ultimately when you are writing down in terms of the stress component, you are breaking down into the velocity gradients in incompressible flow condition, and we are getting the Laplacian term. So here also, you just in the next step we write. So in order to tackle the turbulence closure problem, we do like introduce one term called the eddy viscosity or the turbulence viscosity. This will show now how it is coming. So eddy viscosity or turbulent viscosity is not a vector property. It is just to counter the turbulence closure problem, and will be denoted as mu t. The value may change from flow to flow. So the T subscript denotes that it is like to account the turbulent flow. Now, in general, when you write down, let's say the rho, the general equation is rho d q dit in the index notation minus del t del xi. I'm neglecting the body force for now. Del xj mu, let it be like here, del ui del x. Okay. So this part, like everyone of you are like acquainted with the index notation, Zubair, you have also done graduate with the right? So this part, if we now we can say the pressure we know is the isotropic part, and this part is like the anisotropic part. So here we basically like write the Reynolds stress term into two components, isotropic and anisotropic here. Before that, like let's say we assume here the turbulent conditions are isotropic. By isotropic mean that the fluctuating components, the square or like let's say just define it, u dash square equal to v dash square equal to w dash square. So the mean of the square of the fluctuating components are equal in all directions. Okay. So now many times we write the small k. Small k is the turbulent kinetic energy. So the this k is defined as, let's say, half into u dash square plus v dash square plus w dash square. When it is isotropic, we can write like all these components are equal to each other. So we can write c by 2 u dash square. So this we can write as k for the isotropic conditions. So you can see, like in this, you can see this part, right? Yes, no problem. So just like earlier, when we wrote down the general one minus v delta ij plus 2 mu Sij, the Reynolds stress components also you can write in this way, minus 2 by 3 rho k delta ij plus we can write like 2 mu t Sij, eventually it will drop out. Instead of that, here we are just simply writing mu t lui del x bar. So essentially we are keeping in like here, let's just write first the mean component rho d y dt equal to minus del t del xi minus del xi 2 by 3 rho k. So this part will be the isotropic part, and we have seen that when we have broken down the time tau yx, we will be writing like this, right? So this is the isotropic part plus this one we said like is asymmetric. So let's say mu, or rather let's write like this del xj mu del y del xj bar. So this is the p bar. Now, this rest of the components here, you can see we have written 2 mu t Sij, or rather in this case it will be an oval bar here Sij. So this is the Reynolds stress here, and if we write in this way, we will be getting this plus mu t del y del x. And this mu t we just said that it is the turbulent viscosity. So now if we like let's, so this is the isotropic part, this is the anisotropic part. So let's say del xj, then together write mu plus mu t into del y, the mean is there here, del y del x. So here you can see that mu plus mu turbulent, as if someone is adding up some sort of viscosity to the fluid. So generally, like from this part is the viscous part, right? As you can see here, due to the introduction of this mu t, we are like as if acting that there is certain increase in the fluid viscosity. So normally we know that the turbulent, like when we measure the friction for let's say a pipe flow, like A RE. So in pipe flow, let's say we can keep the pipe entrance very smooth, and then we cut down the transient to turbulence part, like we can push the transient to turbulence part as high as possible. So let's say we are measuring at 10,000 here. This is 64 by RE. Let's say for is a very like advanced kind of inlet condition, so that we cut down the water resistance, we keep the transition as high as possible. We know for the turbulent cases it is 0.3164 R into the power minus 1. So for the same Reynolds number, you know that the turbulence for the turbulent conditions the friction factor is much higher. So as if this mu t is adding up to the fluid viscosity and like responsible for the increase in viscosity and the eventual increase in the friction factor. Physically, like we know all that it is parabolic profile here, and in comparison, we know that due to the lots of eddies, there is intermixing going on, there is transverse mixing in the perpendicular direction. So, roughly when we draw the turbulent flow for let's say a pipe, it's look like this. The maximum velocity is lesser than this one, and most of the part it is uniform like axial flow. Only in these regions there will be very high velocity gradient. Normally friction factor we just say like at least the one shear, let's say what we write du del y, right? So here and at y equal to 0. So here you can see it is much smoother gradient compared to if you look at turbulent conditions, the velocity gradient is much steeper. That is leading to the increase in the friction factor for a like the turbulent. And this mu t again, please keep in mind this is not a metal problem. It is just like happening due to the emerging procedure. Okay, so in this way we are introducing the turbulent viscosity part. So let me just write down like ooziness is the person the turbulent PD viscosity. So he introduced this concept again. Like if you recall, is the same ooziness on its honor. Like in natural convection, we discussed the ooziness hypothesis. Is the same guy who introduced the ooziness turbulent viscosity concept. So I just write down this about it. Mu plus 4 turbulent into du I del J. So everyone there will be overward side. This is the general equation here. So when we are measuring the Reynolds stress and the viscous stress, the distribution will be looking like this. I just am drawing a rough image. You can see in WS book, or I can send you like the Pope's copy also, where in the wall bounded flows the distribution is exactly given. So here, like the viscous stress mu Ku bar y, let's say, in a pipe flow, this is let's say 0.2 and this is 1 y by delta. The viscous stress is very high near to the wall and then it falls down, virtually becomes 0, very near to the center. So this is for like these results are basically done by DNS of Professor John Key, who is in Stanford or MIT. John Key is Center for Turbulence Research in Stanford. So these guys they did like lots of DNS simulations in pipe flow, and obviously they also measured with the experimental papers, which I can't recall the experimental papers, but at least the simulation results they well validated the experimental results also. So this is the viscous stress part, and the Reynolds stress part, like y by delta, let's write down like this minus rho uy mu dash. So this is again 0.2 here. So this roughly looks like this. So I am not sure about the exact peak position, but what happens in case of the Reynolds stress is that, like, the Reynolds stress is very minimal in the very near to the wall, and then it little bit away from the wall it picks up, and then just like the viscous stress it is falling down as it goes towards the center line. So these are roughly the stress distributions. Again, I am saying the stress is not actual stress, but just for the sake of nomenclature, I am writing like this. So these are the rough distributions of both viscous stress and the Reynolds stress across it. This is the center line. So half of the right. This is y by delta 1 means the center line. So from 0 to 1. So this is y by delta. The radius if we say is the y by delta. Okay. You can also compare like flow over wall also. Just instead of channel, it's a flow over wall. There will be some boundary there also. Very near to the wall, the viscous stress will be there. Slightly away from the wall, there will be emergence of viscous stress. As we go away from the wall, both the effect of the viscous stress and the Reynolds stress will disappear. So now, how about the Fusines introduce this stability viscosity? How to like quantify this term? So then comes the concept of Frankel's mixing length hypothesis. So when like Frankel was scientist or was alive, kinetic theory was very much a happening thing. So this hypothesis was like he built up this hypothesis based on the kinetic theory of gases. So in kinetic theory of gases, you know that the individual molecules they kind of move around randomly, and then like once in a while they will collide with another atom. So in general, like statistically, the average distance over which it moves unhindered before the collision, that is called the mean free path. Mean free path. So let's say the mean free path is defined as the lambda, and like let's say one molecule is moving with u velocity, and then as it goes along the lambda distance till the collision, the change in u over the path lambda. So this lambda is very small, that's why will be using like some sort of Taylor series approximation. We are saying the delta u is equal to lambda del u del y. Okay. Now we said that there are many eddies, like a multiple scale of eddies, and they basically what Frankel suggested that due to this existence of so many eddies, they mix with each other, and basically lots of momentum exchange takes place. So he like said that basically the mixing length, what is he saying? Like let's say reference length scale over which the mixing of momentum is taking place, and that is driven by what he is saying. Let's say this rho u dash v dash, these are arising out of the momentum task due to the fluctuating components. So these will be basically the driving parameter for determining the mixing length. What he says, like if we take into account this concept delta u equal to lambda into del y, so let's say the mixing length is denoted as LA. So now we say when we say that this u dash, we can say that it is scaling like ln del u bar del y. So lm is the mixing length, and the change, whatever change is happening, the effective change lm del u bar del y. Likewise, when we are like making our life simple by taking the isotropic condition, we are considering that u dash b, this is anyway, sorry, this will be always 0. Like let's say u dash beta square, they are equivalent to each other in isotropic condition. Then the net change of b dash will be also, since u dash and b dash are of similar order of magnitude, we are saying the change of b dash will be also del bar del bar. Okay. So in this way, you can write. Let's just write in this part. So the product of b dash b dash is ln square. You can write del u bar del y square. Anyway, even if you don't write mod here, it is fine. You can simply write bracket of del u bar del y square. But on the next step, when we are writing minus rho u dash b dash kind of thing, then we already have shown that in general u dash b dash quantity, the Reynolds trace is a positive quantity. So then we can write rho ln square. Let's keep one mod sign like this, del u bar del y and del u bar del y. So let's not get obsessed with the plus minus sign here. This we have done to keep this quantity at least a positive quantity. So since like in this one, this is a material property, this is a positive quantity. So ideally the turbulent viscosity, we are trying to take it as a positive quantity. So here, because we are taking it as a positive quantity, because we know that the dissipation is higher in case of the turbulent condition. That's why mu t like is aligning physically, that we have to make it positive. Never it happens that the friction is decreasing in turbulence, right? So that's why in order to show the enhancement of the dissipation effect, we take to keep this as positive. So therefore, we can say that in terms of the mixing length, the turbulent velocity, turbulent viscosity is rho Lm square del u bar del y. So this is like the rough approximation for the turbulent viscosity, and later he also like what about how it is like Ln, how to determine that. So one ad hoc assumption you can say, not very foolproof. That time it was like when Prandtl or von Karman was doing the research. So let's say they wrote like this, or you can write this as K also. So this is the von Karman constant, 0.4 its value for a for the flow over a wall. So this value is called Karman constant. So again, like the turbulent viscosity itself is like varying from flow to flow. This is just valid for the flow over the walls. This A or this, what is this Greek alphabet called? Yeah, so this alphabet value, this will vary from different flow scenarios. Okay. For the flow over a wall or within a 5 flow channel flow, we can keep this value as 0.4 of the y, and y is the distance from the wall. So y is the distance, the orthogonal distance from the wall. Okay, so first we saw the turbulence closure problem. Then in order to tackle the turbulence closure problem, Bouzinès floated the idea of turbulent viscosity. Basically, the Reynolds stress was decomposed into, just like the normal stress component, we decomposed into isotropic and anisotropic part. And the anisotropic part introduced the concept of the turbulent viscosity as mu t. Then, in order to get a quantitative estimate of this mu t, Prandtl suggested that we adopt the concept of the kinetic theory of gases. His hypothesis was the mixing length hypothesis. So mixing length basically represents the physical distance over which momentum between the two, like two or three different eddies is taking place, the length scale, and this length scale is denoted as Lm, which turns out to be finally like the connecting point mu t equal to rho Lm square del u bar del y. Okay. And then we said that again, this is not a foolproof one because this mixing rate itself is dependent upon this variable. This variable can change from in different flow scenarios. Okay, so now we can get an universal picture in terms of non-dimensional coordinates, at least for the flow over the wall. So that is like we will try to characterize the flow near the wall, and we will try to write in terms of some non-dimensional parameters. So this characterization will be helpful when we are, like, let's say, analyzing flow with any bounded flow, channel, pipe, or any square cross section, or flow over a simple flow over a flat wall. These concepts will be useful. So before that, like, let's say we are denoting as the wall shear with something called friction velocity. So rho, normally, like when we define the coefficient of friction, we write like this: tau w by half rho u infinity square. Here, in like utilizing this concept only, we are characterizing the wall shear as the product of rho into the. So this is the friction velocity u tau. Sorry, this is u tau friction velocity. So this friction velocity is friction with V tau is tau wall by rho. In this way, we are defining the relevant length scale for the flow over the wall in turbulent conditions. The turbulent length scale here is mu by u tau. Mu is again meter square per second. This is in meter per second, so it is a dimensionally, like you can see, the if we divide this unit by this unit, there will be 1 meter unit. So it is dimensionally constant. Okay, and normally we write like mu del u bar del y very near to the wall. So we'll come to that. So very near to the wall, earlier we showed that Reynolds stress is virtually absent. There is, like basically what he said, the wall like acts as a damper, and due to the presence of the wall, the turbulent fluctuations are very minimal. So we'll be not considering the Reynolds stress component, only the velocity gradient, the mean velocity gradient. When we are like characterizing the shear stress very near to the wall. So very near to the wall, virtually no Reynolds stress. The wall shear is the right is predominantly due to the gradient of the mean velocity component. Okay, there is of course some Reynolds stress, but it's like much lesser compared. Like if you compare the order of magnitude, then this is way higher compared to the Reynolds stress. So then you can write like tau w. So this very near to the wall. Let's say if we take a like simplistic assumption that u is varying linearly with the wall, we can write mu into the mean velocity component by y y is again like in the y direction. So this is the y. Okay. Then we can, let's say, do some algebraic manipulation like this: y tau mu by u tau, and we divide here. This mu is taken in this side. What we will do is u bar by u tau and y by y tau. So you can see here what we are doing. We are dividing the u bar by the friction velocity. So that's why here also one u tau is coming, because this is coming in the denominator of u bar. Similarly, we are dividing y by the y tau. Okay. Yeah.
What is the difference between this y and y tau?
Yeah. Let me just. I think I didn't write down the y tau. So y tau is this one only actually. This is the y tau. So this is u tau. This is the terminal length scale we are defining as y. This y tau, we are writing this formula, that is nu by u tau. This is as it is. This again, these non-dimensional ratios of u bar by u tau, here defining this as u plus, and the ratio of y by y tau, this we are referring as y plus. So this becomes u plus, this becomes y plus. So you can write here tau w by, please note here, this is kinematic viscosity, this is dynamic viscosity. So nu by mu is becomes 1 by rho, right? So then rho u tau square. This is u plus y plus. Again, if you remember, the u tau square is nothing but this one. U tau is this, and u tau square is this quantity tau 1 by rho. So essentially, you can see that if we look this quantity is u tau square. So u tau square by u tau square equal to u plus y plus. Okay. So this side becomes 1. So very near to the 1. U plus equal to y plus. So here, and this, like this is called the viscous sublayer. So essentially this sort of name is like given because we are essentially stressing on the fact that there is hardly any Reynolds stress, only whatever the term is coming out, that is happening due to the mean velocity gradient. So that's why u plus y plus. So many times, like people, like without going into the intricacy k epsilon k omega or k SST omega, at least my students from Nath earlier, he always used to say that it is always better to use the k SST omega model for the wall bounded flows, because like this region is from 0 to 5. In order to resolve the flow very near to the pipe flow or any like bounded flow, we need to resolve this area. Because let's say we are doing the validation purpose and we are like simulating the quantity, we are plotting u versus y versus, right? So very near to the wall, if we get a like when you are plotting u plus y plus from 0 to 5, you should get a linear profile. I thought you were doing. So that is like if the like first of all, we need to resolve the profit in such a way that this is a very physically this is a very small quantity. So the meshing have to be done in such a way that we have enough data here, so that we can like let's say the physical meshing is such that y plus equal to 5, let's say. If we convert it into some physical dimension, let's say it is y equal to x1. Your meshing is minimum meshing is x2, which is greater than x1, right? So if such kind of meshing happens, you'll never be able to resolve the flow near the wall, and you have no way to validate what is actually happening, like u plus y, u plus equal to y plus. That information you will be never able to get by the simulation technique. So, like this is the viscous sublayer. Again, in some old books, it is called laminar sublayer. Nowadays, no one uses laminar sublayer because people say that there are still some like fluctuating components. It's just that for our approximation, we are neglecting those terms. So nowadays, it's mostly called viscous sublayer. So let me just draw the graph little by little here. So u plus versus y plus. This is 5. So 0 to 5 is u plus equal to y plus. Then 5 to 30 is some sort of like, let's say there is no as such any proper like algebraic form. People try to like obtain some sort of power law scaling. This is the intermediate region. Some sort of this is called the buffer layer, where people just use some normal like power law scaling. And like once you exceed the y plus greater than 30, what the experimentalists of the simulation guys say that the component of the mean velocity gradient then almost becomes zero or becomes much smaller compared to the Reynolds space. Outside this y plus greater than 30, the Reynolds space is much more dominant. So that's why when we try to characterize this region, we will be only taking the Reynolds space component, not the mean velocity component. So this region, let me just write down here u plus equal to y plus 0 to 5. So like these things are like most frequent, not necessarily it has to be exactly 5. These are the approximate observations. Let's just write in this region as u plus equal to f y plus, and this region, so this is the viscous sublayer. The intermediate region is the buffer layer, and this region we just derive. So this outside this region is called the log law region, and the formula governing in this region is called the log law of the wall. So this is log law of the, yeah. So outside y plus greater than 30, Reynolds stress is dominant. So we can write the contribution of the walls here. Let's say we write down minus rho u plus e dash like this, and we can write use the mixing length concept. So rho ln square mu bar del y square, and we'll use the formula involving the carbon constant. So you can write ln equal to ky. So as you can see, that very near to the wall, y is also very small. Mixing length is also very small. As we go like away from the wall, y increases. Ln square will accordingly increase. So then you can see that we are writing mu t equal to rho ln square del u bar del y. Okay, so you can see this mu t, this is varying. This is not a constant material property like the typical fluid viscosity which is used. So let's say then we characterize like this: tau w equal to rho k square y square del u bar del y square here. We take this one here, right, like this k square y square del u bar del y square. Now please remember the walls here by rho is the square of the friction velocity. So yeah, it's still written u tau square is tau 1 by rho. So let's write here the tau 1 by, sorry, not this one. This, where has written? Oh, here only. Okay, sorry. So this formula is right here. So tau 1 by rho is u tau square equal to k square y square del u bar del y. Now, if we just take the root, we can write, let's say, ky del u bar del y. Following that, like I am not writing down the intermediate steps, you can show that 1 equal to k y plus du plus dy plus. So there are like 1 or 2 intermediate steps you can easily carry out that conversion. So du plus equal to, you can write 1 by k du plus by y plus. Following that, you can carry out the integration 1 by k ln y plus a here. So as you can see that outside the y plus there is the logarithmic dependence of y plus. Since there is a log component involved, that's why it is called log law of the wall, and it's generally observed greater than 30, and this k is the Theodore von Karman. So that person who was again PhD student of Rantel only, but Karman himself, he later went to from Germany, he went to US, and he himself did also a lot of things in aerodynamics. But nevertheless, this is known as Karman constant. I don't know, it's not named after any famous scientist, it's just a constant. This is like around 5. So people will do the simulations or experiments like this k, like 0.35 to 0.45, and this one is like not exactly 5, it's like 5 plus minus 0.5. So these are the, like, when someone tries to simulate the flow near the pipe, these are the guidelines based on which you can carry out the calculation. That let's say, like near to the wall, we know the formula u plus v y plus out. So this region, it has some sort of scaling relationship. You can find out, like if you like do the literature survey of flow in like 1 domains, you can find out the scaling relationship. Some people have tried to given a formula. in this log region, this is the governing formula. So in this way, like there are three regions. One is the viscous sublayer, one is the buffer region. The buffer region is basically the region where both the stress components are like equivalent with each other. In the log law region again, the mean velocity gradient is much less dominant compared to the Reynolds stress, and in this way there are these three layers very near to the wall. Okay, so this is again, this derivation is just done assuming that the wall is very smooth. Sometimes there can be flow over very rough walls. So in that case, like let's say if the roughness can be quantified some mean quantity, like let's say in this case, like some sort of undulating surface, if the mean height is s for a flow over a rough surface, and s is the mean roughness height, then in the log law region you can write 1 by k ln y by s plus b. Again, you can see instead of y plus, it is normalized with this mean roughness height. B is again a constant. B I don't remember. Obviously, this B will again change from scenario to scenario depending upon the mean roughness height. So, just another quantity I wanted to just discuss, just like the turbulence, there is also the intensity or degree of turbulence. Let's just write that. So I equal to one third of u dash square plus v dash square plus w dash square by some sort of characteristic velocity or fixed velocity, center line velocity, whichever is like for flow over a wall, this u infinity represents a fixed velocity. For pipe, some sort of mean velocity. This is the like it will divided by u infinity. In case of isotropic, by definition, these three quantities will add up and they are equal to each other. So isotropic, again I am reciting the definition. So this quantity becomes 1 by 3 into 3 u dash square by u infinity. So eventually it becomes the u dash square. So these three gets cancelled out by u infinity. Okay. And you remember the kinetic energy is 3 by 2 u dash square. So u dash square for the isotropic turbulence, you can write like this 2 by 3 kinetic energy. Okay. So the intensity is again like if we have information about the kinetic energy, we can write this I as 2 by 3 kinetic energy by u infinity. This is the intensity of the turbulence. Okay, so anyway, there is maybe I can spare just spare me 1 or 2 minutes. So just writing down the 2D flow over a flat wall. So 2D flat plate boundary layer flow, if you recall that the basic equation is rho into del V plus, we are dropping out the steady state term, you can write u del u del x plus v del u del y equal to minus 1 by rho dp dx. So if you recall, into the flat plate boundary layer, it was shown by order of magnitude analysis that del p del y is 0. So therefore, you start with the assumption that p is a function of x and y. Then, since you are showing that p is not a function of y, you are converting the partial derivative term into ODE term. So you are writing like this dp dx plus, again, if you recall, we are only writing del to u del y square. So basic. Oh, sorry. Yeah. So here, like if you recall again, by using order of magnitude analysis, we start with the viscous terms del to u del x square plus del to u del y square, and then we show that the second order derivative with respect to y is much higher than this term. We drop out this term, we keep only this term. Then if we carry out the Reynolds evaluation procedure here, so we turn out it will be like this: u bar then u bar del x plus v bar then u bar del y equal to minus y by rho dp bar dx plus, again here let's write like this, no, del y mu plus mu t del u bar del y. So these guys I wanted to like just writing because I just thought last week only the 2D flat plate in the convective transfer course, the turbulence, the counterpart for the turbulent flows over same set of geometry will be like this. So that's a brief discussion of like how we like tackle the some sort of approximate expressions for the flows over the walls, and we'll meet at, depending upon the lunch, if it gets over by 1:30 we can meet at 2. If it gets little delayed we can start at 2:30 maybe, so that I can just give the that presentation from 2:30 to 3:30 at max. You will just wrap it up with the like the things which you can do in future for maybe 20 minutes around.